Hello guys, today we're going to be talking about divergence. But first, we got to explain the concept of a vector field. A vector field is basically a function that maps any coordinate on this coordinate plane to a specific vector. Let's take a look at an example. So here, I have this amazing simulation pulled up. I don't know who made it, but I'll probably link in the description. But you can see that every single point here is associated with a vector. I know it doesn't really show like every single point. That's to reduce clutter on the screen. But when I have this vector field, in this case, this is f of x comma y is equal to x comma y. This vector field looks like this, all right? And the vectors that have, these brighter colors on the outside, that represents that they're really like long in their magnitude. So their colors represent the magnitude, and that's just to reduce clutter on the screen. But you can see that vector fields assign every point to a specific vector. Now let's take a look at why does this function look like this. So we're going to go back to basics here. Let's say that I plug in the point 1, 1. All right, so if I'm plugging the point 1, 1, that means I'm focusing on this coordinate right over here, right? 1, 1. And notice how I get a vector of 1, 1 as the output. That means that there's going to be a vector with a length of 1 on the x direction and a length of 1 on the y direction. If I plug in the point f of, let's say, -1, 1, that's associated with this point right over here, right? F of -1, 1 is this point. And so my vector is going to be, well, it's the same thing as the input. It's going to be -1, 1. And so you can see that a vector of -1, 1, well, what does that look like? Well, I'm moving -1 in the x direction, and I'm moving 1 unit up. So overall, the vector is going to look like this. And I can do the same for these 2 points, so let me just do that real quick. So you can see that after I've drawn, a couple points on my vector field, you can kind of get the gist for what's happening. As you move away from the origin, right, it looks like that, you have arrows that are just pointing away from it. And so you can think about the origin or, the vectors around the origin as sort of diverging from it. All right. So imagine if you just took like a snapshot. Think about it. A snapshot of vectors that are around this origin. And this origin, we can say that this acts kind of like a source, right? It's kind of like a source. So you can imagine like a water bucket in Minecraft, right? If you like spill that water bucket, it's going to start flowing outwards like so. And so this origin can be seen as like a source for all these vectors expanding outwards. And when a point acts like a source, that divergence is going to be positive. Now, in contrast to this, if you have the vectors pointing inwards towards the point, this point will now act like a sink, all right? And in this case, our divergence would be negative. And by the way, if you just want to see an example of a sink, well, take this vector field, right? -x, -y, and you see all the arrows are pointing towards some point, which once again is the origin. And divergence is really popular. So if you're really interested in physics, let's just say that, I don't know, you have a positive charge, right? You might have learned this in physics when you're doing like electromagnetism and charges. And you might recall that positive, charge has this like electric field around it that kind of represents what an imaginary positive test charge would feel if it was placed somewhere here. So for example, if I have a positive charge here and I place another positive charge here, well, positive, they want to repel each other. So this charge is going to move away from it, hence why the arrow is this way, right? Or if I place, a negative charge right over here, a negative charge is attracted, or a negative charge would have things attracted to it, right? So imagine if I place a positive test charge, right over here, right? This is my test charge. Well, if I have this negative charge right over here, this positive test charge is going to be attracted to it. Hence why the arrows are pointing towards it. So, if you're interested in physics and things like that, you'll see concepts like these pop up really often. So this is going to be the divergence formula. It looks really, really intimidating, but don't worry, we'll break this up into simple parts. And so let's start out with simple examples. So say that I have a vector field, x comma y. I'm going to take you through, the calculations first, and then we can explain, why this formula even works in the first place. So let's say if our vector field is once again this x comma y, where, the vectors are like pointing outwards from the origin. I want to calculate the divergence of this. And so what you do is you take the partial derivative of the x component of this vector with respect to x, and then the partial derivative of the y component of this vector with respect to y. So essentially, right, this right over here, this x right over here just represents, the x component of my vector field. And then this right over here just represents the y component, right? And so, the derivative of x with respect to x, that's just going to be 1. And then it's going to be added to, well, the derivative of y with respect to y, that's also going to be 1. And so the divergence is 2. And this makes sense. We have a positive divergence because we are diverging, and it actually doesn't matter what point we choose. And the reason why is because, well, divergence just measures net flow. So divergence measures sort of net flow. This is the key idea. All right. So let's say if I have this, tiny vector field, or not tiny vector field, but a simple example. Let's say if I'm looking at this point right over here, there's a vector coming into this point, and there's this vector going out of this point. Now, what do you notice about the divergence of this? Would you say the divergence is positive or negative? Well, the divergence of this point would actually be positive. It would be positive. Because remember, divergence represents net flow. And so if there's sort of longer vectors coming out of this point than into the point, then, well, the divergence is going to be positive, right? If there's more coming out than there is coming in, then, well, there's going to be a net flow outwards. You're still diverging. And so now we can make sense of why this vector field, x comma y, has a constant divergence. We can make sense of this because let's examine the points that are around this point. Let's say this point has the coordinates -3, 3, meaning that our vector associated with this point is going to point like this. Now, if I look at another point, -2, 2, right? Well, that's just going to be, at this point right over here, there's going to be a weaker arrow associated with that, right? The magnitude of this arrow is going to be less than the magnitude of this arrow, right? And if I were to look at a point that's after this vector, after -3, 3, in the same direction. So if I look at this point, -4, 4, look at this point, -4, 4, notice how the arrow gets larger. And so notice how there's always going to be a net flow in this direction for this example. Let's consider divergence in 1 dimensions. So in 1 dimensions, divergence, a positive one, would be when there's a net flow to the right. Well, a negative one would be if there's a net flow to the left. Now, let's say that if we're considering this point, which we can say this is f of x, because remember, this is only 1 dimensions, so we only need a vector of, input of one thing, right? So for our vector field, we only need one input. And likewise, this point right over here would just be f of x plus some distance across this number line, which I'll call delta x. All right, so this is this point. Now, you can think about f of x plus delta x as sort of the net flow, or sorry, the flow outwards, right? And you can think about f of x as the flow inwards. So what we do is we would subtract these two values to get the net flow, right? So the flow outwards minus the flow inwards gives you the net flow. So f of x plus delta x minus f of x gives you the net flow. And if we want the net flow per unit length, so we want the net flow per kind of distance that we traveled, well, we're going to divide all of this by delta x, right? This is going to be the net flow per distance that we traveled, okay? And so this right over here, well, you might remember this as a derivative if we make the limit of this, limit of delta x approach 0, right? As we essentially as we essentially make our point that we're examining and a point close to it, as we make it closer and closer to each other, the net flow per unit length, right? So how much we're, kind of flowing out per unit that we're traveling, well, that's going to get more and more accurate. And if we do that, from this, vector field, it might be pretty clear that, well, we're going to end up with a positive divergence. There's going to be a net flow that's going to be going towards the right in this case. And so that is the intuition behind divergence and why it has derivatives. It's because you can imagine there's like a box around the point, and well, you're kind of examining points around it and seeing, well, how does the net flow per unit vary if I take a tiny step in the x direction? And for 2 dimensions, well, it's the same idea, right? You would just take, well, the divergence in the x direction essentially, and the divergence in the y direction, right? You can kind of break it down into 2 parts, because recall that for a vector field, right, you're going to have 2 functions, right? You're going to have a function that represents, the x component of your vector field, and then a function that represents the y component of the vector field. And so if we take the divergence of both of these sort of individually, it's kind of like in physics where, if you have an x component and a y component, you can kind of treat it like individual problems, right? Because the x component does not affect the y component. And after that, we just add it together. So sometimes the divergence can actually vary point to point, unlike, with linear functions when the divergence is constant. And so how would we do this? Well, it looks like our x component here, right? If I want to take the derivative of x squared y with respect to x, I treat the y as a constant, I do the power rule, and I would get 2xy. And then for my other part, this is going to be the f of y part, right? The vector field in the y direction. And so if I take, derivative of this, partial derivative with respect to y, I will just get 2y plus x. If we want to find the divergence at 3, 3, well, we just plug in 3 in for x and 3 in for y, right? And so we get 2 times 3 times 3 plus 2 times 3 plus 3. And so this is going to be 9, that's 18, plus that's going to be 6 plus 3, that's 9, and overall the divergence there is 20.